Hello, my dear students. This is Assistant Professor K.C. Hanchinal from Department of Electrical and Electronics Engineering, CCAP Institute of Engineering and Technology, Vijaypura. But basically, in today's session, we are going to discuss about the analysis and performance of a three-phase induction motor. From exam point of view, this is very important concept. So, before proceeding or before studying the analysis as well as the performance, we need to understand what is induction motor. Okay, induction motor means what? It is basically as you already familiar with the basic construction of the induction motor. Induction motor will be having the two windings itself, or the two parts itself. Which are those? The main parts are stator part as well as the rotor part itself. Is it right? So we can define it as an induction motor. It is an AC electric motor, okay, in which electric current in the rotor part, rotating part, which needed to produce the torque itself. How that torque it is going to be produces? The torque it is going to be produces by the reaction between, which are the factors? The torque which is produced between the reaction of varying magnetic field which is generated in the stator and current which is induced in the coils of a rotor itself. Due to this, what will happen? The torque it is going to be produces. That is going to be called it as what? Induction motor. So, and even this induction motor, it will run less than that of the synchronous speed itself. So synchronous, why it is going to be running less than that of a synchronous speed means in the sense that if there is a slip, this is a very important term. The slip, then only it is going to be called it as a induction motor. All induction motors will be having the slip. Otherwise, that induction concept will not be applicable itself. Getting my point? So the new term, what I had considered here, slip itself. What is the meaning of slip? Slip, it is nothing but it is the difference between the synchronous speed and the actual rotor speed to the what? Synchronous speed itself. Or we can also define it as a slip is equal to synchronous speed, ns minus n divided by the ns itself. Getting? So now, okay, let me start the session now. Analysis and performance of a three-phase induction motors. Basically, three-phase induction motors are of two types are there. Which are those? The first one, it is squirrel cage induction motor. One more is slip ring induction rotor itself. Getting my point? Slip ring induction rotor, it is also going to be called it as what? Wound rotor induction motor. Correct. So what is the basic difference between the squirrel cage as well as the slip ring induction rotor? So first, let me consider in squirrel cage induction motor, the rotor will be consist of longitudinal conductor bars. So these conductor bars are going to be shorted. So these conductor bars are going to be shorted by the circular connectors at the two ends itself. While in case of a wound rotor, the rotor it is also having the balanced three-phase distributed winding itself, and which will be having the same poles as that of the stator winding itself. Getting my point? However, in both squirrel cage as well as the slip ring or the wound rotor, the stator it is going to be carries the three-phase balanced distributed winding itself. Keep it in mind. Which kind of a winding will be there? Balanced distributed type winding will be there in case of what? Squirrel cage as well as the slip ring induction rotor. Okay, let me start with this analysis and performance now. So we can observe it in this diagram. This is the per phase stator, which is referred equivalent circuit of an induction motor itself. So now here in this diagram, so basically we know that, so this is induction motor, it is also like that of the transformer itself. In case of a transformers, we will be having the primary winding as well as the secondary winding itself. Like in this also, induction motor, it is having the stator winding part as well as the rotor winding itself. Keep it in mind, okay. This is the stator part and this will be the rotor part and this will be the magnetizing component itself. So this is having the resistance and the reactance. RS is nothing but the stator resistance and this will be the stator reactance itself. Getting my point? Here RR dash and XR dash are nothing but what? These are the stator referred values of a rotor resistance RR dash and the rotor reactance XR dash. Getting my point? RR as well as the XR nothing but the what I told here, this is the stator part and this will be the rotor resistance and this is the stator reactance itself. This XR dash as well as the XS dash as well as the RR dash divided by S. This is nothing but what it is, the stator referred values of a rotor resistance RR and the rotor reactance XR itself. Getting my point? So this is the basic equivalent circuit of the three-phase induction motor. Okay, now slip, how we are going to be define it as, what is the definition of the slip, what I told? So this is the basic difference between the synchronous speed and the actual rotor speed to the synchronous speed itself. Getting my point? So how we'll define it now? Ns minus n divided by the ns itself, is it? But when we consider with respect to the angular velocity or nothing but the this omega ms, it is nothing but the angular synchronous speed to the rotor speed divided by what? Angular synchronous speed itself. Getting my point? So this is going to be the speed, it is going to be expressed in terms of what? Radian per second. So now we know the definition of this synchronous speed, angular synchronous speed. So omega ms is equal to 2 pi ns divided by 60. As we already know that omega is equal to 2 pi n divided by 60 itself. But with respect to the synchronous speed I am considering, that is the representation of S stands for what? Synchronous speed, angular synchronous speed. So that is the reason 2 pi ns divided by 60 here. And what is the formula for the synchronous speed ns? Ns is equal to 120 f divided by p itself. Now this ns you substitute here. 2 pi divided by 60 into ns, it is nothing but 120 f divided by p here. Now how much you will get? 60 here, 2 2 4 itself. 4 pi f divided by p here. So this is the unit of this synchronous speed will be radian per second itself. 4 pi f divided by p here, where f it is nothing but the frequency and p is the number of poles itself. Getting? Now we got it for the what? Synchronous speed now. So we know that this formula, slip is equal to omega ms divided minus omega m divided by omega ms now. So now we'll multiply here. So yes, this multiplied here, omega ms is equal to omega ms minus omega m itself. Now see here, we know the formula for this one. Omega ms is equal to, how we'll write now? So we'll take omega m will be equal to this omega m, will take it on the LHS side. Then what will get it on the RHS side now? Omega ms minus s omega ms here. Now omega m is equal to, here in this omega ms is the common what I had taken outside, into bracket of 1 minus s here. Okay, I hope you got how we got this equation. But in the book, in the textbook, directly they had given it as a, so this one directly they have taken as a omega m is equal to omega ms into the bracket of 1 minus s itself. So how we got this explanation, what I had written here. Okay, now we got it as a omega ms into the bracket of the 1 minus s itself. Now let me consider this one from the figure 6.1b. So for this figure it is nothing but 6.1b itself. This is nothing but the equivalent circuit, nothing but the stator per phase stator referred equivalent circuit of the induction motor, nothing but the simplified circuit. So how this simplified circuit, how we have drawn in the sense that here the stator impedance drop is very negligible compared to this terminal voltage itself, capital V. So then the equivalent circuit which is going to be simplified and what I had drawn here. Okay, so now from this figure we can write the equation for the IR dash, it is nothing but the rotor current which is referred to the stator itself. Referred which side? Referring to the per phase stator values. Keep it in mind. Rotor current which is referred to the stator. So now how will write the current now? IR dash is equal to this terminal voltage V divided by RS, which are connected in a series manner. So that is the reason RS plus RR dash divided by S plus J, it is nothing but the reactance terms. Reactance terms XS plus XR dash itself. So as we know that this is the resistance part plus reactance part itself. So this will give the current. Which current? The rotor current, which is referred to the which side? Stator side itself. Getting? Next thing it is the power which is transferred to the rotor. The power, whatever the power which is going to be developed, which is transferred to the rotor, and then that is also going to be called it as what? Air gap power itself. That is why it is represented by what? PG. Nothing but what? Where the air gap will be there? In between stator as well as the rotor part, small gap will be there. That is going to be called it as a air gap itself. The power which is developed in that particular gap, so that is going to be called it as a air gap power itself. As we already familiar with the power formula, what is the formula for power? Generally, I square R itself. Now, this is the 3-phase induction motor, and that is the reason 3 IR square dash I square R. I square means which current? This is the rotor current referred to the stator. IR dash square into what it is the referring to the stator side. So rotor side RR dash divided by S itself. So that only the power which is developed in the air gap, what I had written here. Next thing it is, at the same time the losses also produced. So whatever the losses, will get it on the rotor side. The rotor copper loss will be represented as how? PCU itself. So copper loss will be represented as a I square R itself. With respect to which side? Rotor side itself. 3 IR dash square into RR dash. Getting? Now, so whatever the electric power it is going to be developed, so that power it is converted into the mechanical power itself. How we'll get this mechanical power means PM is equal to, when we subtract from this power developed in the air gap with this and copper losses, when we subtract from this one, we'll get the mechanical power itself. The PG minus PCU. Then substitute this PG what it is there? 3 IR dash square into RR dash divided by S minus 3 IR dash square RR dash itself. When we subtract, we'll get the equation like this. So this will give what? Mechanical power itself. Once we got the power, means we can easily calculate the torque developed by the motor itself. What is the formula for the torque? Torque will be the ratio of the power divided by the what it is? Omega m, it is nothing but rotor speed itself. Power to the speed. Torque, keep it in mind, torque is the ratio of the mechanical power to the rotor speed itself. PM divided by omega m itself. Then what is the formula? What we got it for the PM now? Substitute this PM. Now 3 IR dash square RR dash into the bracket of 1 minus S divided by S divided by omega m itself. What is the formula for omega m? So here it is there. Omega m is equal to omega ms into the bracket of the 1 minus S itself. After substituting over there, we'll get it as a, just to simplify it, you will get the equation like this. Torque is equal to 3 divided by omega ms IR dash square into RR dash divided by S itself. Getting? I hope you are getting this one. Once we got the torque, now what we have to do? This torque we got it as a T is equal to 6. Call this equation as a 6.9. Now torque is equal to T is equal to 3 divided by omega ms IR dash square. So we know the formula for the IR dash, is it right? So now you substitute this one. Substitute here, we'll get it as a V square RR dash divided by S divided by RS plus RR dash divided by S whole square plus XS plus XR dash whole square itself. Nothing I had done here, just I have substituted for this IR dash square in the torque equation itself. This IR dash square will get it from the equation number 6.4 over there. Okay, we'll get the torque itself. Getting my point? Next thing it is. Next, what we are going to do here. So this is the basic comparison of the equation 6.5, where the equation is there 6.5. 6.5 is the power which is developed in the air gap itself, PG, and 6.9 itself. 6.9 where that equation is there, this is the torque itself. So now Now we know the torque equation. Torque with respect to the power, mechanical power to the rotor speed I had taken here. But the power which is developed in the air gap, we can write like this. T is equal to Pg divided by omega ms here. But here what I had taken? Power developed. PM, mechanical power to the rotor speed. Here equation what I had considered here? Air gap power to the synchronous speed. Getting my point? So here rotor speed I had taken, here the synchronous speed I had taken here. So now when we done the comparison, what we'll get? So we can do the comparison. So now, so the motor output torque at the shaft which is going to be obtained. How the motor output torque it is going to be obtained? In the sense that by deducting the friction, windage as well as the core loss torque itself. Getting my point? The motor torque at the shaft which is going to be deducted. How it is going to be deducted? The losses due to the friction, windage and the core loss. When we subtract it means we'll get the, from the developed torque we can subtract these losses means we'll get the motor output torque at the shaft itself. Getting my point? The developed torque, whatever the torque we have produced, whatever the torque it is going to be produces, which is the function of a slip only. So what I told, so this is the torque completely, whatever the torque it is going to be produced in the induction motor, it is the function of the slip only, from the equation number 6.10 itself. In the here the where the equation is there, 6.10, this equation here, in this what we are going to do, differentiating that equation, differentiating T, that is nothing but torque in equation 6.10 with respect to what? Slip itself, yes, and equating to 0. What we have to do? Whatever the torque which is produced in the induction motor, which is the function of the only slip itself. What is slip? Slip is the difference between the synchronous speed and the actual rotor speed to the what? Synchronous speed itself. Completely the torque which is developed in the induction motor, which is the basically function of the slip only. Then what we have to do here, that is the reason the equation 6.10, it is going to be differentiating with respect to what? Slip s. Then we need to equate it to 0. When we have done like that means we'll get the maximum slip. The slip power for the maximum torque, Sm, this will be equal to plus or minus. Plus in the sense that this is for the motoring operation and minus in the sense that this is the braking operation. So when we have done differentiating T, torque with respect to S, and when we have equated to 0 means we'll get the equation like this. Sm is nothing but what it is? Slip for the maximum torque itself. Here the plus and minus sign indicates what? Plus it is for the motoring process and negative indicates for the braking process. Getting my point? We'll get the equation for what now? This is the slip for maximum torque over there. Next, what we need to do, substituting this equation, whatever the equation we got it for the slip for a maximum torque, from equation, substituting from equation 6.12 into 6.10. So this Sm, where the S term it is there, this is synchronous speed, R dash divided by S it is there now. So instead of this S, I had substituted over the this Sm, what I am going to substitute it over there. When we substituted in that torque equation means we'll get the maximum torque. T max is equal to 3 divided by 2 omega ms into the bracket of V square divided by Rs plus or minus root of Rs square plus Xs plus Xr dash whole square. Getting? This will give the maximum torque itself. Getting? So now we'll take the ratio now. This torque, it is going to be expressed. The torque, it is going to be expressed in terms of Sm, nothing but the slip for a maximum torque, and T max itself. Getting my point? So now, so based on this, we can draw the nature of speed as well as the torque. Here the omega m it is there, omega ms it is there. Nothing but the synchronous speed, and this will be the rotor speed itself. The speed torque and the speed rotor current we have taken here. So this is the curve for like a hyperbola. It is there, omega ms with respect to the torque and omega m with respect to the rotor current itself. This is the characteristics, the nature of speed torque characteristics we have drawn here. Next thing it is, so one important ratio we have taken here. So equation 6.10, so the torque equation where it is there, here in the torque equation T is equal to, so equation number 6.10 it is there, 3 divided by omega ms, 3 divided by omega ms into the bracket of the v square rr dash divided by s divided by rs plus rr dash divided by s whole square plus xs plus xr dash whole square itself. When we torque T divided by T max, if you had done means, we'll get it like this, 2 into the bracket of 1 plus rs divided by rr dash into sm divided by T max means s divided by sm plus 2 times the rs divided by rr dash into sm itself. Then we multiply here, 2 into 1, 2 plus 2 times the rs divided by rr dash sm itself. This 2 times rs divided by rr dash sm, it is going to be gets cancelled here. Then what is remaining now? So only the remaining term is 2 divided by s divided by sm plus sm divided by ss sum. So this is the ratio of what it is, T divided by T max. Therefore maximum torque it is. Torque to the maximum torque when we will get by considering the slip for the maximum torque over there. I hope this is clear to all of you. Thank you.